The string, the spring and the pulley shown in figure are light. Find the time period of the mass m, right? Now let's say the system is in equilibrium position initially. So if the system is in equilibrium position, so the net force on the mass m will be equal to 0. So the tension that will be in the spring can be written as mg. Fine. This is the initial tension at equilibrium condition. Fine. And the same tension will be at this very point. And if I draw the free body diagram of this point A, then T will be equal to kx1 initially at equilibrium condition. Right. Now let's say I stretch the spring, or let's say I bring the block downward by a distance of y. Okay. Then at that moment I can write T2 minus mg is equal to mass into acceleration. That is, if I bring the block by a distance y downward, then a spring force will act upward, tension will increase. This new tension, let it be T2. So T2 minus mg will be my new acceleration towards upward, right? Now this mg can be written as T1. So this will be T2 minus T1 is equal to mass into acceleration, and this T2 can be written as k into y. Fine. Now T2 minus T1 can be written as k times of y minus x1, that is equal to mass into acceleration. Fine. Now this y minus x1 is nothing but the distance between the equilibrium condition, at that moment the spring was x stretched, and the extreme position. At this condition the spring was y stretched. So this y minus x1 is nothing but the amplitude. So it can be written as k into amplitude is equal to mass into acceleration. So k by m into amplitude will be equal to acceleration. Now again acceleration is directly proportional to amplitude or displacement. So this k by m will be equal to omega square. So time period comes out to be 2 pi under root of m by k. That is the answer.